When the bombers of the German Luftwaffe flew against the British Isles in 1940 to launch the Battle of Britain, the coast of England was studded with a series of tall wooden towers which had been erected some 2 years before. Within shelters associated with these towers, military personnel intently watched the glowing faces of cathode ray tubes and communicated with interceptor control points and anti-aircraft batteries. As the attacking planes approached the British coast, fighters took off to meet them, and anti-aircraft crews manned their guns. The German squadrons found the British forces alert and ready, and in the following months of the Battle of Britain, the Luftwaffe was decisively beaten back. Never, said Winston Churchill, had so many owed so much to so few. Never, he might perhaps have added, could so few have repulsed the fury of the German assault had it not been for those wooden towers and those glowing tubes. For this was radio location, as the English called it, in its first spectacular operational test. Radio location, which robbed the attackers of the great military advantage of surprise and allowed efficient centralized control of the defensive forces, contributing mightily to the British victory. But although this was radio location's first great challenge and triumph, the basic theory of its operation had long been known. During the 1930s, scientists in the United States, France, and Germany, as well as Britain, had independently developed workable systems. In this country, much of the early research and development was done at the Army's Fort Monmouth Signal Corps laboratories, and during this period, many important achievements were recorded by a small group of dedicated men. Concurrently, significant discoveries in this field were made by scientists of the Naval Research Laboratory. In 1938, the SCR-268 was initially tested by the Coast Artillery. Desired at first as an aid in the aiming of searchlights, it was soon applied to the directing of anti-aircraft guns as well. In 1939, the longer-ranged SCR-270 and 271 were developed by Fort Monmouth for the Army Air Corps as early warning sets. The United States called these systems radar, for radio detection and ranging, a term that is now universally accepted. Our early sets utilized the longer waves of the radar spectrum, requiring large, cumbersome antennas for even short-range operations. In 1940, British scientists came to America with the newly developed magnetron tube, which could produce high-power pulses of short-wave energy, permitting antennas of more manageable size and a higher degree of accuracy. At the Massachusetts Institute of Technology, the U.S. set up a radar research unit to supplement the Army and Navy laboratories. Britain and America pooled their radar efforts, and with that collaboration began the history of modern radar. Radar works because radio energy transmitted outward from an antenna will be reflected or echoed back by obstacles encountered in its path. By means of a directional antenna array, the radiated energy can be focused into a narrow beam or lobe, making it possible to determine the direction or azimuth of any target seen by the radar. If the energy is radiated in separate pulses, the time it takes a pulse to reach the target and its echo to return indicates target distance or range. Search, target acquisition, and surveillance radars scan the sky or surface in various patterns to keep broad areas under observation. Tracking radar is designed to keep one target continuously centered in its beam. Some radars can be used for either search or tracking purposes, and a recently developed system called Track While Scan allows the tracking of targets which are being observed by search radar. Continuous wave, or CW radar, employs separate sending and receiving antennas and is not a pulse signal. It is chiefly used to measure target speed, a radar capability which results from the Doppler effect. Because of this Doppler effect, the reflection from a target moving toward the antenna will be of shorter wavelength or higher frequency than the transmitted signal. The return from a target moving away from the antenna will be of greater wavelength or lower frequency than the transmitted signal. By comparing the transmitted and return frequencies, the speed of the target can be computed and moving targets discriminated from stationary ones. This shows the Doppler shift principle applied to CW radar. Pulse radar can also take advantage of the Doppler effect to observe moving targets and measure their speed. This moving truck will reflect a signal pulse of a different frequency than the transmitted pulse. Some pulse Doppler radars measure the frequency shift occurring within the echo alone, without reference to the transmitted signal. In this instance, reflections from terrain obstacles, the moving truck, and the faster moving wheels will all be of different frequencies, depicted here by the thickness of the waves. By measuring these differences in frequency, the radar can detect the moving target, gauge its speed, and even in some cases, recognize its nature because of the characteristic way it changes the return frequencies. Frequency modulated, or FM radar, varies the frequency of a continuously transmitted signal in a fixed pattern. Target distance can be computed by relating this pattern to the amount of modulation appearing in the reflected echo. Radar indicators display target information in various ways. The A-scan indicator displays the single dimension of range, resulting from the time difference between the pulse indication, or main bang, on the left and the target reflection pip on the right. This range line becomes a circle in the J-scope with target distance measured along the circumference. The B-scope displays two-dimensional information. Here, azimuth is indicated to left and right of the center line, and range increases vertically from the baseline. The PPI scan, or plan position indicator, plots range as distance from the center of the circle and azimuth as degrees of the circle. There are other scans for other purposes, and to obtain three-dimensional information, indicators are often used in combination. The basic components of a typical radar set are a synchronizer timer, transmitter, antenna system, receiver, indicator, and power supply. The timer, or synchronizer, which is the heart of the radar set, synchronizes the system in the dimension of time, so critical to radar measurements. The transmitter supplies the radio frequency signal to the antenna, and in pulse radar, the spillover from this signal appears as the main pulse on the indicator. The antenna system radiates the signal, picks up the target reflection, and delivers it to the receiver. The receiver amplifies the weak reflection many millions of times and relays it in proper form to the indicator. The power supply services each component. There are additional electronic circuits and servo systems for controlling antenna movement. When the Japanese brought World War II to America by their attack on Pearl Harbor, an SCR-270 radar set gave the warning. A warning, however, that went tragically unheeded by military forces not yet accustomed to undeclared war. During the embattled years of the Great War that followed, the radar art was advanced by leaps and bounds as American and British groups, always far ahead of the Axis powers, developed radar applications of great scope and variety, which assisted in gaining ultimate victory. At first, radar was largely used for air warning systems and anti-aircraft fire direction. If radar could detect enemy planes, it was obvious that friendly interceptors would also appear on the scope and could be led by radio to their targets. Thus, ground-controlled interception was devised. The development of IFF equipment for identification friend or foe allowed radar operators to challenge their targets electronically and from the reply on the radar scope to differentiate between friend and enemy. Airborne radar for fire control came into being, first only as a range indicator to aid pilots in daytime gunnery or to warn them of rear attacks by the enemy. Then in more sophisticated versions, as in this tail gun installation on the B-29. And finally, in the Black Widow night fighter, the radar became the eyes of the pilot, leading him to the enemy plane and indicating when it was time to fire and break off the engagement. One of the most versatile and accurate of World War II radars was the Signal Corps' SCR-584. With both search and tracking capabilities, the SCR-584 could establish target azimuth or elevation angles within an error range of 1/20th of a degree and a distance within 25 yards at maximum range. This microwave set used a parabolic reflector of high gain or focusing power. Many SCR-584s are still in service today. Some U.S. anti-aircraft batteries equipped with the SCR-584 averaged an enemy craft down for every 40 rounds of ammunition expended. The SCR-584 was also used for longer-range search missions. Fighter bombers in tactical sorties over Europe after the invasion were tracked in poor weather by SCR-584s and radio-guided to their targets. Radar was applied to other bombing techniques by the British and Americans. For night raids over the Ruhr Valley, British Pathfinder planes were equipped with radar beacons, which amplified radar reflections for easier tracking. 2 ground radars in England, tracking the Pathfinder, could lead it to the target city where signal flares were dropped to guide the following bomber fleets. In the American shore-end system, the radar was carried aloft and the plane's position determined by the aid of radar beacons on the ground. The accuracy of this system was demonstrated when, by its use, our bombers discovered an error in the map position of the island of Corsica. With America's so-called Mickey radar, the ground echoes were utilized to map the terrain below as a basis for pilotage and blind bombing through clouds or overcast. Of the 400,000 tons of bombs dropped by the 8th Air Force after 1943, more than 1/2 were radar aimed. A sector view shows the radar picture of the ground passing beneath the plane during a bombing mission. In the Pacific, some 110,000 tons of Japanese shipping were sunk in 1 month by the 14th Air Force bombers, all at night and all by the aid of radar. The U.S. Navy also developed radar techniques for target search and fire control against air and surface targets. cases, enemy vessels were sunk without being sighted, except as targets on the ship's radar. Other naval radar uses included convoy control, search and rescue operations, and harbor security. Applying radar techniques to the anti-submarine campaign in the Atlantic aided substantially in achieving the 1943 mark of about one sinking a day, with most sightings made by radar. Other radar applications under early development during World War II included aerial navigational aids, weather mapping, radar altimeters, and air traffic control. When in the last months of the conflict, British radar stations began picking up fleeting echoes from the German V-2 ballistic missiles, the problems that would face future radar development were foreshadowed. Following World War II, radar developmental work continued in government and private laboratories, improving, refining, and expanding on the many pioneering achievements of the war years. And applied to radar systems were new electronic discoveries, such as the powerful klystron tube, wideband amplification of microwave frequencies, and low noise receivers. It became apparent that radar echoes brought back a lot of information about the reflecting objects. The problem was to find ways of extracting this information most efficiently. As military weapons became more and more complicated and entered into areas of great speed and precision, radar played an increasingly important role because of its ability to gather data at the rate of accuracy required. And to assimilate and react to this data, electronic computers and automatic servo systems began to displace the human factor in operation and control. Today, as at its inception, radar is still most widely applied to air defense, as in the giant SAGE system. This system is designed to provide at a central command post a continuous depiction of airspace traffic over the U.S. and Canada. The basis of most of the information fed into the SAGE system is radar observation. Stretching some 3,000 miles across the top of the continent from the Aleutians to Iceland are the dew line or distant early warning radars. Erected with great difficulty in the bleak and remote Arctic, these long-range search and acquisition radars scan the polar regions on the lookout for hostile planes or air-breathing missiles coming in over the roof of the world. The antennas turn within plastic radomes whose surface is kept free of ice and snow by interior heat lamps. Dew line installations are connected together and to the SAGE system by radio circuits on which target information can be instantly relayed to the central NORAD command post. Flanking the dew line in Alaska and Greenland are new high-power radars with immense 300-foot-high toroid section reflectors. Part of the BMU's our ballistic missile early warning system. These radars can pick up their targets at a range of 3,000 miles. This vast range, with all the special electronic problems it imposes, is necessary because of the lightning speed of modern missiles. Backing up the dew line are two other radar fences, the Mid-Canada line and the Pine Tree line, so that targets moving south can be kept under constant surveillance. Also tied in with the North American Defense Network are the radar barriers guarding our ocean approaches. Navy picket ships maintain a constant vigil far at sea off our coasts. Texas towers standing on slender legs above the waves offer a platform for the radar sentries. Radar is borne aloft by Navy and Air Force planes, and their searching beams scan the skies to great distances over the ocean. Picket submarines can range the polar seas even above the dew line as advanced outposts of the radar warning system. Radar is designed primarily for search and target acquisition, whether guarding North America or other parts of the free world, or designed for battlefield use, have similar characteristics. A typical example of this type of radar is the AN-FPS-36. This high-power microwave set has a typical paraboloid section antenna reflector. The array can be set for continuous circular scan. The range of this radar is 200 nautical miles. A rectangular waveguide for transmitting the microwave pulse with minimum line loss connects the antenna horn to the equipment within the permanent shelter. The set is designed for fixed installation. The indicators include an A-scan presentation for target range determination, and a PPI scope for azimuth and range. A moving target indicator, when switched on, can electronically remove unwanted stationary echoes from the scope, and the presentation can be altered to show a narrowed range of search for nearby targets. A similar version of this set with slightly less range, the TPS-1D or TPS-1G, can be readily transported and set up in the field. Height-finding radar is much like search radar, except that it scans vertically instead of horizontally. The characteristic appearance of search radar is maintained even in this immense 120-foot wide version, the FPS-24. If search radar guarding the ramparts of our continent should pick up an unfriendly intruder, the information would be relayed to a regional control center, and from there to the central NORAD command post, from where would come the decision for action. One of the family of weapons involved in air defense is the manned interceptor. Radar-supplied information on location of the interceptors and the intruders is fed to computers from which emerge the data which is transmitted to the interceptor pilots. In the most advanced system, the plane is actually flown automatically by command signals supplied by the computer. As the range closes, the plane's radar takes over, leading the pilot to intercept and automatically triggering the air-to-air missile. In many cases, a third-stage radar directs the missile to its target. The Navy's Sparrow, in one of its versions, is a semi-active homing missile, tracking the target which is illuminated by the launching plane's radar. Airborne radars are often versatile units for fire control and navigation. In this system, there is a gun aiming scope at the top and a B-scope at the bottom. A friendly IFF response is shown appearing on the B-scope. Here, the B-scope is used as a navigational aid, showing terrain features. This airborne search radar can be used for fire control, navigation, and storm avoidance, and in conjunction with a sonobuoy for anti-submarine warfare. At various strategic points in the U.S., missile master radar and control centers are being set up in conjunction with the SAGE system to coordinate the operations of the Nike batteries in the surrounding area. Missile master sites have powerful radars for target surveillance and height finding. Here, targets acquired independently or passed on from SAGE units are allocated to one of the missile batteries for destruction. Air traffic in the area is monitored on numerous indicators, which selectively display the information picked up by the radar. Under missile master control are the Nike Hercules and the shorter range Ajax. The Nike weapon system utilizes radar for target acquisition, target tracking, and missile tracking. After the target is acquired, the target tracker locks on. The missile radar then locks on, and the computer then indicates when the missile can be fired. In the control center, the positions of target and missile are indicated on the scopes and traced by recording pins as the computer feeds command guidance instructions to the missile by coded radar pulses. The Nikes carry radar beacons to permit more positive tracking than is possible from only skin reflection. And then, the kill. Special capabilities against low-flying targets are built into the Army-developed Hawk missile system. The Hawk's radar is specially tailored to its mission. The Hawk system includes a pulse acquisition radar for normal target search, a CW acquisition radar with its special ability to separate moving and stationary targets by the Doppler effect, and a CW illuminator or tracking radar, which can hold on targets even at treetop level. The Hawk, which can be fired from fixed or mobile launchers, has a semi-active homing system, which causes it to dive down on low-flying planes, directed by the reflections bounced off the target by the CW illuminator radar. Operational details of anti-missile missiles are largely classified. But this view of the large radome at this Nike Zeus test site indicates that radar will certainly contribute importantly to this essential program. Since surface targets are stationary or slow-moving, radar in this area is used to monitor only the position and speed of the missile, so that it can be guided to conform with a predetermined trajectory or visual sighting, as here with the Army's Lacrosse. In the guidance system of this Intercontinental Range Atlas, tracking radar monitors the early flight path as a basis for trajectory corrections, which are transmitted to the missile from a ground computer. Radar is also essential for tracking test missiles downrange from Cape Canaveral into the South Atlantic and for the recovery of nose cones and instrument packages. A powerful new radar, the FPS-16, has been mounted aboard a naval vessel for such missile tracking operations. Depicted here is this radar's tracking ability on a jet fighter traveling 460 miles an hour at 10,000 feet. The plane is slightly off-center because the antenna is tracking a radar beacon in the left wingtip pod of the jet. At the Army Signal Corps laboratories, this 50-foot antenna bounced a radar echo off the moon, providing this A-scope view of the actual occurrence. A new 60-foot antenna with automatic tracking capabilities is being developed for the tracking of weather satellites. This huge 84-foot diameter antenna, developed for MIT's Lincoln Laboratories, supported by the Armed Forces, is capable of skin-tracking Earth satellites and has probably established a record by bouncing an echo off the planet Venus, a round trip of some 56 million miles. A recent Navy radar development called Project Madre uses relatively long waves to get ranges up to 2,600 miles by bouncing the waves off the ionosphere, both on the way out to the target and on the way back. This system can be very important in picking up hostile missiles at point of launch. But all radar developments have not been concerned with missiles in space and anti-aircraft protection. During the Korean War, the MPQ-10 mortar locating radar performed distinguished service in the tracking of enemy mortar shells as a means of directing counterfire. Servo controls drive the antenna array for horizontal or vertical search, as well as during automatic tracking. When a target appears on the B-scope indicator, the operator places range and azimuth lines over the echo. The J-scope then monitors an area 1,000 yards on each side of the echo position. When the second round appears, it is centered in the J-scope and the unit switched to automatic tracking. From the track trajectory of the round, location of the enemy mortar can be determined for directing counter-battery fire. A later mortar locating radar, the MPQ-4, can accomplish the same result by observing only one enemy mortar round. This set alternately radiates upper and lower beams, and the mortar trajectory is computed from the 2 points at which it intercepts the beam. The MPQ-4 can track enemy artillery as well as mortar rounds, and can locate the impact point of friendly shells for fire registration. In the area of battlefield surveillance and mapping, radar techniques are providing some important advances. Manned aircraft with side-looking radar antennas fly over the battle zone, taking electronic pictures of the enemy positions to be photographically reproduced or transmitted by radio back to ground commanders. Unmanned drones, propeller or jet-driven, can be remotely guided on similar missions. The drones, which can be radar tracked for guidance and recovery, also carry forward-looking radar for obstacle avoidance. Amazingly high-resolution pictures can be obtained of the ground layout by these airborne surveillance radars. If desired, only moving targets are shown, and development is underway on methods for providing three-dimensional pictures to give contour effects to the radar views. A ground-based surveillance radar, the TPS-25, takes advantage of the Doppler shift between echoes reflected from stationary and moving targets to detect enemy personnel and vehicles. Using a scope and an audible indicator, trained operators monitor only the Doppler shift frequency, which indicates the presence of a moving target and its speed. With practice, the characteristic Doppler patterns of many targets can be identified. A man can be picked up at 5,000 yards, a vehicle at 20,000 yards. A similar unit, the TPS-33, also has an audible and visual indicator. Antenna position gives target direction. Range information is obtained by an electronic gating system, which can be adjusted to monitor echoes returned from selected distances. This system has further been adapted for this lightweight, portable, silent sentry radar. This unit can pick up a walking man at 1,000 yards. The Army is experimenting with a handheld unit, the PPS-6, for use by infantry patrols and frontline troops. A snap-on A-scan display can be used with this model to supplement the audible signal. Another new concept in radar is the development of a tactical long-range surveillance radar with mobility. This system combines an improved version of the AN-FPS-33 radar with a unique folding butterfly antenna. The butterfly antenna can be erected by 5 men in 15 minutes. Radar has brought planes in for landings during low visibility conditions for many years, using the ground-controlled approach system. This military GCA unit monitors azimuth, elevation, and range, indicating the position of the aircraft in relation to the runway and allowing the operator to talk the pilot to touchdown. Ground-based radar that can spot a rainstorm at 250 miles is being used for local weather forecasting. With a range and height indicating scope, a side view of the storm can be presented along with a plan view to give the three-dimensional weather depiction. Hurricane hunting planes of the Navy regularly patrol the Caribbean during the season to get radar pictures of the giant tropical storms to aid predictions of their course and velocity. A special radar unit has been developed by the Signal Corps for determination of cloud base height and overcast thickness. Radar is a navigational aid of first importance for civilian merchant ships. Radar is carried to indicate the position of nearby vessels, to map the coastline or harbor, and to pick up buoys, which are now being equipped with radar beacons. A newly developed ship radar shows other vessels in the area with telltale wakes behind them to better indicate their speed and direction. Radar units are used by small boats and pleasure cruisers as navigational aids. The antenna is located on the center line of the boat, and the search area is displayed on a small PPI scope in the cabin. Doppler radar mounted beneath the airplane has solved the old problem of accurately determining the aircraft's ground speed and drift angle. Radar beams angled from below the plane measure the forward and sidewise speed of the plane along the ground. The measurement is so accurate that the pilot has a constant indication of his latitude and longitude, or his course can be traced automatically on a chart. In other systems, the Doppler measurements are used to show the aircraft position on a map grid projected on the windshield. Aircraft also use radar absolute altimeters and terrain avoidance radar to indicate mountains ahead. All this then and more is radar and its applications, an electronic beam extending man's ability to observe and record, searching vast sweeps of distance to bring back millions of items of data per second to help man to see, to control, and to tame the environment of hurtling speed his science has created. In the future, radar eyes will more completely direct the traffic of our crowded airspace. Collisions will be automatically prevented in the air, on the sea, and perhaps even along the ground. The family car may be controlled by a radar beam scanning a strip of metallic paint, coded to give speed and location data. Radar defense sentries will detect aggressor planes or missiles anywhere in the world and direct counter missiles to destroy them in flight. Our military commanders may observe enemy positions depicted in 3 dimensions on huge screens and direct defensive fire by guided weapons. Radar will reach into space to lead man on his greatest adventure and bring him safely home again. The exciting world of the future, in fact, can scarcely be envisioned without granting a place of primary importance to wondrous radar and its myriad applications.